Hey, welcome back. This is College Algebra 8.1 Matrix Solutions to Linear Systems. And what is this? It is a way of handling big systems of equations. So the first type of system that we worked with, if I can find my pen, would be the two equations, two variables. So stuff like 2x plus 3y is 5, and x minus y is 2, something like that. Then in the next section, we worked with three equations, three variables. 2x plus 5y minus z is 5. X minus y plus z is 2. And then maybe 3x minus 5y plus 2z is 5. But the sky is the limit, folks. Okay, you can literally have 100 equations with 100 unknowns. It happens in engineering. Okay, so we need to have kind of different techniques to handle these bigger systems, and what we do is use matrices, and what that does is kind of gets rid of all the variables, and there's a whole course dedicated to solving these linear systems called linear algebra, believe it or not. And if you keep taking math, that would be like in your second year of math school, you would take linear algebra. So they study it to death, but for us, it's basically just an extension of what we've already been doing, but to higher and higher dimensions. And it makes it. It also gives you the ability to kind of abstract everything you've been doing. So it's not just about this, this geometric picture of two lines hitting each other. It could be applied to many more circumstances. Okay. So anyways, the first thing we want to introduce to you is the augmented matrix. And it's a shorthand way of writing systems of equations. That's all it is. Shorthand method of writing systems of equations. Okay, so let's look at an example like number 5. You'll be given your standard system. So this one's 3 equations, 3 unknowns. And for the most part, we're not going to worry about the 100 equation, 100 unknowns. We just want to introduce this with some easy examples so you know how it works. And then you could get a computer or something like that to do it, and for the hard ones, for the big ones. But you have to kind of know how it works first. Anyways, this is our system. And then 2x minus 3z, this equals 5, this equals 4. So an augmented matrix is basically just the same thing, except we get rid of all the variables. Okay. So in the first row, we're going to put 5, -2, -3. Okay. And then instead of an equal sign, we're going to put this big bar there. Okay. And on the other side, we put what it equals. Okay. And then you just do that for each equation. Make sure they're in line. So the first column has to be for the x's, the second one's for the y's, and the third one's for the z's. So the first one would be 1, and then 1 for y, and then 0 z's, and that equals 5. And then 2, -3, and then, whoops, the middle one's 0. There's no y's. Sorry. 0, and then -3, and then 4. Okay, so it kind of clears out some of the clutter. And all we do with these is basically the same thing as what you've been doing before. It's just it looks kind of weird. You're probably not used to dealing with boxes of numbers like that. Anyways, let's look at number 10. And this time we want to convert back into a system of equations. So first they give you the augmented matrix. And you probably want to pause the video right now to copy down the thing and then see if you can convert it back into a system of equations. So anyways, the system of equations, 7x plus 0y, I'm not going to write 0y, and then plus 4z is -13. 0x plus 1y minus 5z is 11. And then 2x plus 7y plus 0z is 6. Okay. Once we get our augmented equation, we want to do the same things that we've done before, like add, do the addition method. So add two equations to each other, but we're going to kind of do it all at once. And it looks kind of weird. And what we do is call these row operations, but all they are is just kind of the same things you were doing by adding two equations together and trying to eliminate variables. Okay. Okay. So row operations. What are some of the things you could do? You can multiply by non-zero constants. Okay, and the notation for that would be something like 1/4 times row 1. So you have to let the reader know what you're doing. You can add rows together. And you can multiply them too while you're doing that. Add / multiply. Erase that. Sorry. Add multiples of rows together. And the notation for that might be something like 2 times row 1 minus 3 times row 2. And when you get that, this is kind of different. It's going to replace row 2. Okay, so the results of this will end up in the second plate. This whatever you put there, that's where it ends up. Okay, so the results go in row 2. The third kind of operation is not something we usually do. It's just swapping equations. So swap the order. And you'll see why we would want to do that here later. And the notation for that would be something like R1 swap R2. Okay. Okay, so let's just look at how we do these row operations, and then we'll apply it to solve the system of equations. Okay, so number 13, we have a matrix, augmented matrix given 2, 1, 3, -6, 5, 0, 4, -5, 4, and then 10, 0, and 7. Okay, and the book wants us to multiply row 1 by 1/2. It's as easy as you think. So everything in row 1, you just multiply it by 1/2. So 1/2 times 2 is 1. 1/2 times -6 is -3. 1/2 times 4 is 2. 1/2 times 10 is 5. And then everything else is the same. Okay. It's just like what you did with the addition method. It's almost the exact same notation too. Let's look at another one, number 15. 1, 3, 2, -3, 1, -2, 2, -1, 1, 0, 7, 3. This time we want you to add multiples of rows together. So I'm going to go -3 times row 1 plus row 2. And of course the results will end up in row 2. Okay, sometimes when I do these, I like to kind of, and the book probably won't do this, and most teachers won't do this, but I kind of write it up underneath. I'll show you. The things that aren't going to change will be row 1 and row 3. So you can kind of just rewrite those if you wanted. The only thing that's changing is row 2. Okay. So -3 times row 1, and this is where I kind of write it out. After a while, you'll be able to do it. You should be able to do it in your head, but it'll be -3, 9, -6, and 0, and then row 2 is 3, 1, -1, 7. So what is going on here is basically they're trying to cause a cancellation, like we do when we do the addition method. You multiply one or both equations by a non-zero constant. That's exactly what's going on here. They're getting rid of that first variable, the x variable. But anyways, -3 plus 3 is 0. 9 plus 1 is 10. I don't know why I'm doing it in blue at this point. 0 and then 10. And -6 plus -1 is -7. 7 plus 0 is 7. Okay. Okay. Let's do another one like that. Here's a bigger system, more realistic. 1, 0, 2, 5. -1, 1, 0, 1. 1, -2, 3, 2. 1, -1, 4, 4. And again, it's a real nightmare copying everything down correctly. 3, 0, 11, 6. I'm going to stop and make sure I got it copied right. Okay. Okay, this time the book wants us to take -2 times row 1 and add it to row 3. And of course you put it in row 3. You just plug it into the end, whatever comes second. Okay, like back here it was -3, 1 plus R2, so you put it in the R2's position. Okay, but simultaneously they're also going to want us to go -5 row 1 plus row 4. So the only things that change are row 3 and row 4. Row 1 and row 2 are going to stay the same. Okay, so I'll do the -2 row 1 plus R3 above. And I'll do that, I guess, in blue. So -2 times row 1 is -2. 2, -2, -2, -6, and then row 3 is 2, 0, 3, 4, 11. And again, this is about canceling stuff out. So -2 plus 2 would give me a 0 in the first position. 2 plus 0 is 2. -2 plus 3 is 1. -2 plus 4 is 2. -6 plus 11 is 5. Okay. And then -5 times row 1 is -5, 5, -5, -5, -15, and then row 4, 5, 1, 2, 4, 6. So see how, again, they cause a cancellation of that x variable. You're going to get 0, oops, I'll go back to white, 0, 6, -3, -1, and then I believe -9. Okay. Okay, so we're doing these same methods that you did with the addition method and what section was that? Like 7.1 and 7.2, I think. But we're kind of encoding it in a different way. Because we have to deal with huge systems, we need to kind of have a procedure to follow. And it won't be, it's kind of one level away from working with equations. So, okay, so I'll just give you the procedure, what we're after and working with these systems. So solving these linear systems with what they call Gauss-Jordan or Gaussian elimination. So Gaussian or Gauss-Jordan. Okay. All right, so this is how it works, folks. You're going to have some matrix with a bunch of unknowns in it. The first thing you want to do is get a 1 in this first, and they call it a pivot position. Okay, so the pivot positions are along the diagonal. right here. These are all considered pivot positions. And you want to get 1s in those positions and 0s underneath. In order to make that happen, the first thing you want to do is get a 1 in that first pivot position. And then pretty much whatever everywhere else. And then below it, you want to get 0s. Okay? So you get 1, blank, blank, blank. But then you get 0s below it, okay? Using addition of rows. Okay. So once the first column is complete, you go over to the next column and get a 1 in its pivot position. And then you got to get a 1 underneath that. I mean a 0 underneath that, sorry. So the next step, 1, 0, 0, 1, 0, and then everything else, I don't know. Finally, get a 1 in that last pivot position on the diagonal, and you should have this thing. Once it's in that form, you can stop. That's called Gaussian elimination. And generally, that's where I stop. Once you get there, you can jump back into variable land and use your substitution methods, because that last row right here, if you change it back into variable form, it's going to say z equals like 5. So you'll have one of the unknowns, and then you can just back substitute to get the other answers. Okay. But if you don't like that, you can keep going and go to Gauss-Jordan elimination, which will give you row reduced echelon form, which looks like this. So the first thing you want to do is get a 0 on top of the second row. Okay. And then get 0s in that third, sorry, a 0 on top in the second column, and then you want to get 0s on top in the third column. Let's get my rows and columns mixed up. So 0, 0, 0. So you'll get this weird looking matrix. They call that sometimes the identity matrix. And that would be your end. So you would actually have x equals something, y equals something, z equals something, if you were to rewrite it in variable form. So this here is the Gauss-Jordan. Okay, and this, this is the Gauss-Jordan elimination. If you go all the way to here, and you can literally, if you go to the Gauss-Jordan, you can read your answers directly off of the matrix. Okay, so Gauss-Jordan elimination, but I never bother because it's just I just never bother. Okay, so this is the reduced row echelon form. Okay, reduced row. They used to call it row reduced echelon form when the order doesn't really matter. Echelon form. Okay. So that's our goal, and basically all you're doing is adding equations together and eliminating variables, but you're doing it with the matrix, so you don't actually, you kind of lose sense of what you're doing, because now all you're doing is basically arithmetic, But I mean, that's what you're doing. You're doing what you did in 7.1 and 7.2. It's just now it's kind of abstract. Okay, so let's take a look at one of these. This is kind of done for you, and they want you to fill in the blanks. Okay, so 1, 2, 3, -1, 3, -2, 1, -1, -9, and then 8, -2, +9, and then they want you to get to this next step, which is 1, -1, 1, 8. And so the first step to get it in row reduced echelon, or the first step if you're doing Gauss or Gauss-Jordan, is to get a 1 in the pivot position and in this spot. And they already have done that for you. So your job in this first step would be to to get zeros there and there. And you could use that first row to cause that elimination. So for the second row, it's going to be what? Well, -2 times row 1 plus row 2, right? That will get rid of, that'll put a 0 in that position where there's a 2 right now. Then for the third row, you're going to go -3, right? -3 row 1 plus row 3, okay? And then that'll eliminate that. So in this case, you'll end up with 0, 0, 1, 1, and they want you to fill in the blanks here, 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 and here. Okay. So you can pause the video and try that if you want. Okay, so I mean, again, I kind of like just doing them, writing them out. So if you do millions of these, you're going to be able to do them in your head eventually. But for most of us normal humans, I mean, it's not normal, but just, you know, people who don't do math all day long, they're hardly. Shouldn't have said that, but okay. So, anyways, -2 times row 1. So we get -2, and then -2 times -1 is +2, and then -2, and then -16, and then row 2 is 2, 3, -1, -2. Okay. I mean, if you're doing math all day long, you can get awesome jobs. You literally are highly employable, you know. So, yeah. So don't even fret. If you're a math person, more power to you. In the future, you'll be the boss of everybody. Okay. So, anyways, -2 plus 2 is 0. We got that. -2 times row 1 plus row 2. So that shouldn't be a 1. Oh, it's not 1. Sorry, I screwed up. There should be 5. Sorry, I just copied it down wrong. Got a million things going on. Okay, so 2 plus 3 is 5. -2 plus -1 is -3. And then -16 plus -2 is -18. And then -3 times row 1. So I'm also going to write that one out too. I'll do it in a different color. So -3, +3, -3, -24. And then the third row, 3, -2, -9, +9. Okay, so 0, and then, yeah, 1, and then looks like -12. -12, and then, -9 plus -24, sorry, is -15. Okay. Okay, then our next step would be to get a 1 in the second pivot position. So we want to get a 1 here. Okay, and you can multiply to get that 1. So one of the other row operations we do is multiplying. So I'm going to go 1/5 times row 2. So 1, -1, 1, 8, 0, 1, -3/5, -18/5, and then 0, 1, -12, -15. Okay. Then you would want to get a 0 below the 1. That would be your next step. You want a 0 here, and then you would want a 1 where the -12 is, and then we would kind of be done. Okay. So let's actually try to do the whole thing, not just so these problems. We want to go through the whole process now, just given basically a random matrix. So solve the system. We're going to use Gaussian elimination first, and then I'll do one with Gauss-Jordan elimination. Okay. So solve the system using Gaussian elimination. So for this type of problem, in this version, what you're doing is getting 1s on the pivots and 0s below, and ending by sort of doing a back substitution. You have to do the order that we give you. You can't get creative with the order and then expect things to work out. Okay, you got to do it in our way. It's our way or the highway, right? Okay, so let's take a look. 2, 1, 1, negative 1, 1, negative 2, negative 5, 9, 5, and then negative 4, 12, and 8. Okay. Look, so my first job is to get a 1 in this position. Okay, you can multiply it by 1/2, but that's going to cause fractions. Sometimes you need to have, you're going to have fractions, but let's avoid them if we can. So instead, let's do something easier, right? Let's just swap. Let's do a row swap between 1 and 2. So I'll take row, I'm going to swap row 1 with row 2. Okay, so that's easy enough. I just have run 1, 1, 9, 12. 2, negative 1, negative 5, negative 4, and then 1, negative 2, 5, 8. Okay, second step then, I need to get zeros below that pivot position. Okay, I'm going to kill 2 birds with 1 stone here. So to get a 0 in that second row, first position, I'm going to multiply the first row by negative 2 and add it to row 2. And then to get 0 in the first position of the third row, I'm going to multiply negative 1 times row 1 and add it to row 3. Okay. So the only thing that won't change will be the first row. And let's see what we get. So I'm going to write out the arithmetic above and below the arrow. So negative 2 times row 1, negative 2, negative 2, negative 18, negative 24. And then row 2 is 2, negative 1, negative 5, negative 4. Okay. Sorry, I'm just making sure I copied things right, which I didn't. I totally didn't copy things right. I have no idea where I even got my numbers. Oh my gosh, it's driving me insane. I mean, I just don't know where I got that second row, and it's blowing my mind. I don't know where I got it. I made it up. I mean, where did I even get it? Was I looking at a different? I'm sorry, just 1 second. This is mind-boggling. I just don't know. I don't know. I'm sorry. I'm going to have to go back and edit. The first row isn't even right. Oh my gosh. This is what's wrong. Okay, it's all of this stuff. I apologize. Apologize. I'm going to have to redo all this. Apologize. Just get rid of it. I'm sorry. Okay, so let's try again. 2, negative 1, negative 1, 4, 1, 1, negative 5, negative 4, 1, negative 2, 0, 4, and there we go. Okay. Okay, so first swap. Okay, still, we have to get a 1 in that first position. So 1, 1, negative 5, negative 4, then 2, negative 1, negative 1, 4, and I didn't do anything to the third row. Okay, kill 2 birds with 1 stone, right? I need to get a 0 and a 0 in those 2 spots. So what do I need to do? I need to multiply negative 2 times row 1 and add that to row 2. That'll get a 0 there. And then negative 1 times row 1 plus row 3. Okay. So row 1 is unchanged. And then let's get the other rows. So negative 2 times row 1, and I'm going to do all the arithmetic here in blue. So I get negative 2, positive 10, positive 8, and then 2, negative 1, 4. Okay, So that's going to end up being 0 like I want, -3, 9, and 12. And then the third row, again, I'm going to do the arithmetic in blue, so -1, -1, 5, 4, and then I'm adding it to 1, -2, 0, 4. And I get 0 like I want, then -3, 5, and then 8. Okay, so next I need to get 1 in the second pivot position here on the diagonal. So I can multiply by -1/3. -1/3 times row 2. Okay, so 1, 1, -5, -4, 0, 1, -3, -4, 0, -3, 5, 8. Okay, now I want to get a 0 below the pivot position. So that would be right here. I was using blue to do that. Like the first one I used a blue when I got zeros. So a 0 right there in that position. So what do I need to do? I can use the row above it to do that. So it's always use the row above to create the cancellation. So this time I'll have to go 3 times row 2. 3 times row 2 plus row 3. And so row 1 and row 2 stay the same. 1, 1, -5, -4, 0, 1, -3, -4. And then this last row changes. Let me do the arithmetic in blue. 3 times row 2 is 0, 3, -9, -12. And then, of course, row 3, 0, -3, 5, 8. So we get my cancellation like I want. 5 plus -9 is -4. 8 plus -12 is -4. Okay, last step then in Gaussian elimination is to get a 1 in the final pivot position right here. And that's easy enough. I just multiply by -1/4. -1/4 times row 3. Will kind of do it for us. 1, 1, -5, -4. Then 0, 1, -3, -4, and then 0, 0, 1, 1. Okay, so we're not done yet. We still haven't solved it, right? We need to translate this back into our variable system. So we have x plus y minus 5z is -4. Y minus 3z is -4, and then z equals 1. Okay, so now you can back sub. Plug z equals 1 into the previous equation. So y minus 3 times 1 equals -4. Y minus 3 is -4. Y equals -1. And then plop that back into this equation, and you should have your solution. So x minus 1 minus 5 times 1 is just -5, it's -4. X minus 6 is -4. So x is 6 minus 4 is 2, I believe. So our solution is the ordered triplet, 2, -1, 1. Okay? Okay, so it's just a mechanical way of solving these systems. It's nothing new, but you can literally teach it to a computer then, and the computer can solve these systems for you. Okay, solve the system using Gauss-Jordan elimination. So we want to do another one, but this time we'll go all the way to the end of the elimination, and we'll be able to read our answer directly off of the matrix. Okay, so we want to end up with this thing that they sometimes call the identity matrix. 1's on the diagonal, 0 everywhere else. And then our solution is going to be sitting right here, believe it or not. Okay, so let's try one of those. This will be number 29. I'll try to copy it correctly this time. Again, I apologize. Sometimes, I swear. -3, and then -1, 4, -2. Okay, seriously, I'm looking at my paper to make sure it's copied correctly. Okay. Okay, we're good. Okay, so first step would be to get 1 in this position, but we already have it. So our first step is going to be get zeros below. Okay, 2 birds with 1 stone. I guess just negative, right? Negative row 1 plus row 2, and then negative row 1 plus row 3. So you just use that row above to make the eliminations below. Okay, I want to do my arithmetic in blue. So I have negative 1, negative 2, 1, 1, and then 1, negative 1, 1, 4. And then for the other one, it'll be 1, oops, negative 1, negative 2, 1, 1, and then 1, 1, negative 3, negative 2. Okay, here we go. So, first row does not change. Second row, negative 1, 1, 0. I got the cancellation I wanted, negative 3, 2, and 5. Finally then, 0, negative 1, negative 2, negative 1. Okay. Okay. Next, I want to get a 1 in the second pivot position, right here. Again, you can multiply by negative 1/3, but I'm going to just switch the 2 rows and then multiply the row by a negative to get a 1 there. Believe me, I hate fractions more than you could imagine. Okay, so that's what I'm going to do. Okay, so my next step, I'm going to swap row 2 and row 3. Okay, so you get 1, 2, negative 1, negative 1. Then I get 0, negative 1, negative 2, negative 1. And then I get 0, negative 3, 2, and 5. And then I'm going to multiply by negative 1 because you can't have negative 1, it has to be positive 1. Okay? So multiply negative 1 times row 2. Get 1, 2, negative 1, negative 1. And 0, 1, 2, 1. And then 0, negative 3, 2, 5. And then we have to get the 0 below the pivot position. Okay, so again, we need a 0 right here. Okay, so all we have to do is multiply 3 times row 2 and add it to row 3. 1, 2, negative 1, negative 1, 0, 1, 2, 1. And I'll do my arithmetic in blue here. So 0, 3, 6, 3, and then 0, negative 3, 2, 5. And so we'll have 0, 0, 8, 8. And again, we can get another, we need to get another pivot position cleaned. We need a 1 in that position. So I can multiply that row by 1/8, and I even avoided fractions. Okay, so 1/8 row 3, 2, negative 1, negative 1, and then 0, 1, 2, 1, and 0, 0, 1, 1. And now we want to get zeros above. Okay, so zeros above the second pivot. I need a 0 there. Okay, so I just multiply the second row by negative 2. So if you're doing the regular Gaussian elimination, you could have stopped at this point. But because we're doing Gauss-Jordan, now we want to get zeros in the upper, what they call the upper triangular region. Okay, so here I'm going to go negative 2 times row 2 plus row 1. Okay, so 0, 1, 2, 1, 0, 0, 1, 1. Okay, and our arithmetic this time, we're going 1, 2, negative 1, negative 1, and 0, negative 2, negative 4, negative 2. Okay. So we get 1, 0, negative 5, negative 3. And then I need to get zeros above the last pivot. Okay, so I need to get zeros here and here. So you just use the third row to get rid of those. And so what are we doing? We're going 5 row 3 plus row 1, and then -2 row 3 plus row 2. Should get the job done. So we have row 3 as is, and then do my arithmetic. So 5 times row 3 is 0, 0, 5, 5. Row 1 is 1, 0, -5, -3. And then -2 row 3, 0, 0, -2, -2. And then row 2 is 0, 1, 2, 1. And then I do my addition, so this will be 1, 0, 0, 2. This will be 0, 1, 0, -1. And that'll do it. So when you translate this back into an equation, right, you have x equals 2, y equals -1, and z equals 1. That's your solution right there. Okay, so you get 2, -1, and 1, and you are good to go. Okay, so it seems like, why do I care? I can just do this via 7.3 methods, right? But the problem is you're going to have 4 equations, 4 unknowns, 5 equations, 5 unknowns. And sometimes the calculations become astronomical. It's just ridiculous. And you can see all the little arithmetic things going on. It's easy to make errors. Okay, so we definitely want to study this. This type of thing is used in engineering all over the place. The space shuttle needed to have math using matrices and stuff like that. It's just used all over the place. So the methods we used in the previous section won't really cut the mustard, so to speak, for what we need to these what we're doing with all of this ultimately. So we need these other methods to be able to perform other tasks, which are used by engineers and stuff like that. Okay, so it's one level of abstraction away from variable land, and even in that regards, it's interesting to study just now all these numbers removed from their variables. I guess I don't know. I'm just mumbling, I guess. Anyways, I guess thanks for watching, and we'll see you next time.